An interesting consequence of this fundamental theorem of algebra is that if your function has, if your polynomial has only real coefficients, meaning the numbers in front of the x's are all real numbers, they're not complex numbers. They don't have i's in them. If the coefficients just begin with, much like the functions in the previous examples, all have real number coefficients, then something about the solutions is really interesting in that if a complex number is a solution or is a zero of the function, then its conjugate, meaning flip the sign from in between the real and the imaginary parts, is also a zero. So you kind of find zeros for free if your polynomial has complex roots. That being, knowing that, we should be able to go backwards. And if I tell you what the zeros of the roots of a polynomial function are, then you should be able to work back in and come up with at least one function that has those things. And we're going to take advantage of the fact that these roots can be written as factors. So when I look at, if I don't want a polynomial that has these guys as roots, first thing that jumps out at me is that one of these is imaginary, which means that we can also immediately add on to our list its complex conjugate. You could think of 4i as 0 plus 4i. So its complex conjugate is 0 minus 4i, or minus 4i is definitely on this list. So what we can do is we can construct a polynomial that has these things as roots, and we just write it in intercept form or in factored form. X minus the first root, x minus the second root, x minus the third root, and x minus the fourth root. You could leave it in intercept form. There's nothing wrong with doing this. This polynomial would be sufficient, although it's usually better to write it in and assume that you're going to write it in general form, meaning we're going to multiply this out. This isn't so bad to multiply out because we can do it in two parts. The first part I see is I'm going to multiply these two together because they are a difference of two squares. This should be x squared minus 4i squared. And then x minus 0 is just x. And x times x minus 2 is just x squared minus 2x. This guy, 4i squared is 16i squared, minus 16i squared is plus 16. So we can finish this by just foiling this out or multiplying this out, however you're most comfortable. I'm just going to distribute here. X squared times x squared is x to the fourth. X squared times 16 is 16x squared. Look a little ahead because there's an x cubed term here. Minus 2x times x squared is minus 2x cubed. And minus 2x times 16 is minus 32. X. So in general form, here is a polynomial. You could get other polynomials by just taking this thing and multiplying it by a coefficient. You could have multiplied by like an a in front. So all possible polynomials with exactly these roots are of the form some constant times any of these things. Let's try again with these guys. Here are two complex numbers, I and 2 minus I roots of 3. Again, because of this fact, then this real value polynomial function also has minus I as a root and 2 plus I roots of 3 as a root. The smart way to multiply this out and get this in the general form like we did before is not to just put them in this order, but to pair them up in complex conjugates like we did here, because we'll always be able to take advantage of this difference of two squares pattern. So I'm going to write them out as, how about x minus I and x plus I, x minus 2 minus I roots of 3, and x minus 2 plus I roots of 3. This is definitely a difference of two squares. This is x squared minus I squared, or x squared plus 1. This guy might not look like a difference of two squares, but really it is. In fact, if you just, and you can get that by distributing the minus and then regrouping with the x minus 2's in the complex part. So I'm going to kind of do this quickly here. I'm going to distribute the minuses, and then I'm going to regroup each of these as with the real part, and then the imaginary part on its own. You note that the second part is x minus 2. You know, minus times minus I roots of 3 is minus I. And now these are difference of 2. Now this is difference of 2 squares. The only thing, one of the squares is x minus 2, and the other one is I roots of 3. So this is really x minus 2 squared minus I roots of 3 squared, which is x squared minus 4x plus 4 minus 3i squared, or plus 3. So this, a polynomial with these roots would be of the form x squared plus 1 times x squared minus 4x plus 7. Or if I multiply this out, I'm going to use a table. It's the 6. I'm going to get lost in the 6 distributive properties I have going on here. X to the 4th, down across, minus 4x cubed plus 7x squared, down across, plus 1x squared minus 4x plus 7. So it's looking like my general term, my a polynomial is going to be x to the 4th minus 4x cubes. So you like terms, 7x squared and 1x squared is 8x squared minus 4x plus 7. Here's one polynomial with these 4 roots. And again, as we saw in the previous one, you could get many others by just multiplying multiplying all of this by some constant. Lastly, let's find a cubic polynomial. So leading degree, the leading term is going to have an x. This will be x to the 3rd of some sort. It's going to have real coefficients, meaning that the numbers in front of all the x values of x are going to be real numbers, not complex numbers. And has these 2 values as zeros. And we're also going to tack on the stipulation that when you plug in 1, you get 6 out. So this is actually, instead of getting any polynomial, we're going to get a specific polynomial. We know that if these 2 values are roots, then there's a 3rd root. In fact, since one of them is complex, the other is also a complex number, 2 plus I roots of 2. It's complex conjugate. So I know in general all possible polynomials of degree 3 that have these 3 values of roots have to look something like this. If 3 is a root, then one of the factors is x minus 3. X minus 2 minus I roots of 2 is one of the roots. And then lastly, x minus 2 plus I roots of 2 is another root. This is one possible. Note that every possible would be this, but stretched. So maybe times some coefficient a. Let's figure out let's write this in general form. And then once we have that, then we can substitute in this specific value, this x and y input-output pair, and we can figure out what this stretch factor is, what a is. Note, like before, this is in fact weirdly a difference of 2 squares. This is really the same as x minus 2 plus I roots of 2 and x minus 2 minus I roots of 2. So this is, let's see, this difference of 2 squares is like x minus 2 squared minus I roots of 2 squared, which is x squared minus 4x plus 4 2i squareds, or minus negative 2 or plus 2. So this is x squared minus 4x plus 6. And lastly, I'm going to multiply these two terms out. I'm going to get x times x squared is x cubed. Let's see, the x squared terms I'm going to get by x times minus 4x, and then negative 3 times x squared, so minus 4 minus 3 is minus 7x squared. The linear terms I'm going to get by x times 6, and negative 3 times negative 4x, so 6 plus 12x is 18x's. And then the constant term is negative 3 times 6 is minus 18. This is all polynomials that have these guys, all cubics that have this as a root. Thing is, it might be stretched. So I also need to know what this value of a is. But since I know that when I plug in 1, I get 6, this isn't so bad. Note that f of 1, which is a times 1 cubed minus 7 times 1 squared, plus 18 times 1 minus 18 is equal to 6. Let's see, what is this? This is 1 minus 7 is minus 6. 18 plus 8, minus 18 is 0, so this is a times minus 6 is equal to 6. Equals minus 1. What this tells me is that the polynomial that fits this description is minus 1 times x cubed.